In case you're wondering, yes, Canvas is down. The reason Canvas is down is actually because the Amazon server that runs Canvas is actually down. So if you try to go on Amazon right now, you can't see your previous orders and stuff. Yeah, there's some stuff I had to order for you guys. As it turns out, part of Amazon's site doesn't run on their own server series, at least that part of it. And then the like all of the shopping lists are on that, and they're down with our Canvas. Yeah. All right. So this is that problem we just did. Find the pH of the 0.05 molarity trimethyl ammonium chloride. Now, notice that in this problem, we have a weak acid. Can anybody tell what part is the weak acid? Is it this whole thing? That's a salt, isn't it? Okay. So this part right here is actually a strong electrolyte. It's going to split up, right? So you're going to have the chloride come off from this ammonium here. This ammonium here, then, that green hydrogen, that's the acidic hydrogen, isn't it? Okay. All right. So if we look at this species right here, okay, it's going to have a Ka that looks something like this. So our pKa is this value right here. Okay. And notice that in this problem here, we're going to have 0.05 molarity, so it's a pretty dilute solution, but not so dilute that our primary source of H plus is going to be the water, right? So our primary source of H plus is going to be our weak acid, very likely. But this is not a very, very concentrated solution that's going to have a very large ionic strength, right? We're going to have a very small ionic strength because our pKa tells us that this weak acid mostly stays together. We're mostly not going to dissociate. So again, we get our Ka by taking 10 to the negative pKa. We substitute that in. That gives us the Ka, right? All right. So once we have the Ka, we can actually do our math. This is the equilibrium reaction for our weak acid. Everybody see that okay? We'll use that proton. That gives us our conjugate base. Okay. This one is a perfect candidate for our nice assumptions we can make. Remember those assumptions I brought up last time? These ones right here. That we can make assumptions that our concentration of H plus, concentration A minus are going to be the same numbers as long as our acid is not too dilute or our acid is not too weak, right? As long as those two things are true, this is going to be a good assumption. Now, the other thing we can do is we can have the formal concentration minus that same value of the A minus, because that is going to be the remaining stuff that comes apart, right? Okay. So what we can do now is we can use that Ka expression. That's our Ka value right here. This is going to be that products times reactants, but we're going to use the same number because whatever H plus we make is going to be the same amount of the A minus that's left over, right? And that's what's being said in this equation right here. You may notice that this is actually just an ice table. Okay? You are expected to be able to do these faster than you would if you wrote out an entire ice table. Okay? But if you're having issues with these problems, feel free to start with an ice table, which is the initial change equilibrium, right? This would have been the equilibrium column. Okay? We've just shortcut it to the equilibrium column. Okay, and so we have this formula right here. If we go ahead and solve for this formula right here, what we're going to get is this value for x. Okay? Notice that if we solve this the long way, this is going to be the quadratic formula, right? Okay. We can make an assumption here if you want to try, which is that this minus x here will not significantly change the bottom number. Okay? If you make that assumption, you do have to test it later. And so what you would do then is you would solve by multiplying over 0.5, 0.05, and then taking the square root, right? Okay. What you would notice is if you do that and make that further assumption that this x is not going to significantly change that number down there, it works very nicely. Yeah. 10 to the negative 6 is not going to change 10 to the negative 2 numbers, right? In any meaningful way. Okay? And so that further assumption actually makes this really trivial to solve. Okay, once we have this concentration, well, this is the concentration of the A minus, this is the concentration of the H plus. That's both true. And so we can take the negative log of that concentration. That's going to give us our pH, which is 5.55, right? Okay. Anybody have any issues? No? Yeah, this is a straight up General Chemistry 2 problem, isn't it? Yeah. Yeah, we've just wrapped back around to General Chemistry 2. It's just now you know why the assumptions are made and how to make those assumptions appropriately. Okay? And that's the important thing about more advanced sciences. You can make a lot of the same assumptions you made back in general chemistry to do the problems faster, but you need to understand why those assumptions are made, right? Where do they fall apart? Okay? If this concentration had been significantly lower here for the 0.05, if it was like a 10 to the negative 6, 10 to the negative 7 number, could we make these assumptions? No. We would have to do that system with the water, right? Contributing the majority of our H plus. Okay? If this acid right here had been a significantly weak acid, much weaker than this, like a 10 to the negative 20 sort of stuff, could have we made these assumptions? No, again, right? These assumptions would have been bad assumptions. Okay? Okay. Those ones right there are the ones that's hardest to figure out if I messed up. Okay? The other part that is necessary for this is the fact that we're not significantly high concentrations either. Okay? If this had been 0.1 concentrations, 1 molarity concentrations, if this pKa would have been significantly larger, so almost all of this dissociates, we'd have to watch out for the ionic strength too as well. Okay? We'd have to be careful of those. Okay. All right, so weak base equilibria is really just the same thing. We just have a different equilibrium. Okay? So we do the same sort of work. It has the same sort of formulas. Really, everything is kind of the same. The only difference here is, remember, 2 important points, okay? Number 1, this reaction is not the acid reaction flipped, okay? Everybody see it okay? And understand that this does not have the same product here, right? See, there's no H plus at all in this, okay? It is not the acid reaction flipped. So you cannot take 1 over Ka. Okay? Very common mistake people make because that's how you do a flipped reaction, right? You're going backwards. Acid-base reactions are not flipped reactions going backwards. They are, in fact, the reaction going through the water equilibrium, right? And so that's where the mistakes happen. If you want to flip an acid-base reaction, if you want to go from between a Ka and Kb, right? You have to take Kw divided by the Ka to get Kb. Okay? The other part that you need to watch out for here is that whenever you're doing these base reactions, most things are listed in acids. Okay? We do pHs. We do pKas. We don't do POHs and PKBs usually, right? So watch out for that. You're almost always going to have another step where you got to go from the pKa to the pKb. Once you're in pKb, you can do the normal sort of stuff you would do. And then you have to watch out again when you go back, because you're almost never asked for POH. You're almost always asked for pHs, right? So be really careful. Make sure you label everything, because you're going to be doing like, acid prom, acid prom, acid prom, and all some base prom, right? And then you're going to go, oh, same routine. And you're going to get bored, you're going to cross your eyes, and suddenly you're going to report a POH, right? As a pH. Okay? Very common mistake, something you're going to really struggle with. Okay. So right here, again, we have the base reaction. Here we have the base equilibrium. Notice it's the same process. It's just we have OH minus in here, right? And so you're going to be working in OH minuses and KBs, okay? So we can make that same assumption whenever you're not too weak, whenever you're not too small of a KB, you're going to have, again, that same set of assumptions you can make, which is the OH minus equals the BH plus concentration, which you can set both to X, so that way you don't have to solve a series of equations. That means it does the same extraction. You have, again, F, the formal concentration of the base, minus that same X, right? Again, it's just in terms of base, okay? The math works the exact same. The big difference, though, again, remember, X equals in this problem, when you solve it, does it equal H plus? No, it's the OH minus, right? Okay, watch out for that. You're gonna, it really is gonna become an issue. You're not gonna label these when you're doing them on a test, and then you're gonna swap this and get problem wrong. Okay, happens all the time. Okay, so what is the pH of 0.0372 molarity cocaine? Yes, that's cocaine. Okay? One of the original pain reliever drugs. Very effective drug, actually. Also very addictive. Yeah. So they stopped using it. Actually, they didn't stop using it because of addictive properties. They stopped using it because it was addictive and easy to get. Yeah. If you actually want to know the truth. Like heroin and cocaine are not significantly less addictive than fentanyl and opioids that you would get from a hospital. They're less addictive and harder to get in a form that would cause you to become more addictive. Mm-hmm.
So why can't you just do like the negative log of the OH concentration and then just subtract that concentration from 14?
You don't have the concentration of OH minus?
Oh, okay.
Yeah. If you took the pH of the system, you could.
Okay.
Yeah, you could take 14 minus the pH, and you have the OH minus concentration from that. But no, this is a weak base, and so this formal concentration you're given of the cocaine is not going to be equal to the OH minus concentration.
Okay, so that's why you're putting
It in
that
equilibrium.
extra.
Yep, that's why you have to solve the equilibrium instead.
Okay.
Yeah.
Okay. So in that X value, you have to put it under KW.
Only if you have to solve for the H plus.
Okay.
Okay, so there's actually two different ways you can do this part.
Okay.
Okay, there's this way. This is the better way if you're going to just do it the same every time. This is the better way to do it,
Okay.
because then if you need the H plus, you have the H plus.
Okay.
But as long as you're going to think about it for a second first, you can take the negative log of this value, that'll give you the POH, and then subtract 14 minus that value,
Okay.
and that would give you pH. Yeah. But either way works.
Okay.
Yeah. If you want to speed up your solving these, by the way, always try it without first, and then come back if you get something that's within 1% of this. So it's more than 100 times. So this has to be more than 100 times larger than this number. And then you can ignore this number down here. Okay? Yeah. Really makes it faster. It's worth the 5 seconds it takes. Okay. Is anybody having any issues with this at all? Okay. Yeah, it's realistically just Gen Chem 2 when you were solving, got used to do the ICE tables, right? At some point you start solving them faster. This is it. Okay, now the fraction of association, this is the amount that actually is going to be disassociated, okay? And so it's going to be the fraction that is disassociated, right? Or in this case, associated, because we have the base that's taking on the H+. Okay? And so it's going to be the ionized base form divided by the total amount of base in that solution. which would be the formal concentration or the two forms that's in, add together, right? Now, notice that these are fractions. They're not percentages. They do not have a percent symbol. They don't have units, in fact, because they are fractions. And they are something that's less than 1, okay? If you take those numbers and multiply by 100, you get the percentage. And so if you wanted to do the percentage of the association, that would be, in this case, 0.83% of that base has reacted. Okay? Right. Okay, so this is conjugate acids and bases. Again, right here we have our conjugate acid, conjugate base pair, right here. Okay, in this case, the conjugate base right here, conjugate acid right there. Okay, so we have the base going to the conjugate acid. So whenever we have these things in aqueous solution, what are we given again? Well, when we have a strong electrolyte with something like a sodium, potassium, etc., right? These are going to be strong electrolytes. They're going to dissociate into this when they're in water, when they're in solution. Okay? And so this is going to then be our base that we work with. This is then going to be the conjugate acid right here. Okay. All right, now, does anybody have any questions about any of this? Do you need more practice on this stuff at all? Okay, let's start talking about bases, buffers then. Okay, when you have a weak buffer with its conjugate acid or a weak acid with its conjugate base, this is going to form a buffer system. Okay, as long as it's sufficient concentration, you're about middle in terms of the amount of species of each species available, about 50% of each, then you're going to have a pretty strong buffer system. Okay, and so buffers are going to be solutions that resist change in pH when you add an acid or a base. Okay. Or when dilution occurs. Your buffer is again going to be a mixture of an acid and its conjugate base. This means both ways, by the way. You can have the base and the conjugate acid, of course, as long as they're the same species and the same, like, everybody understands what I'm saying there, right? Carbanion. Okay. All right. So, to function as a buffer, you have to have comparable amounts of the conjugate acid and base, typically within a factor of 10. Once you go past about a factor of 100, your buffer system collapses, okay? Just because you have so little of the other species that there's not really any meaning to it anymore, okay? If you mix A moles of a weak acid with B moles of its conjugate base, then the moles of the acid remain close to A, the moles of the base is going to remain close to B. Little reaction is going to occur to change either concentration, and because you're establishing a buffer system. And so they're going to shift to form equilibrium, right? And then what's going to happen is if you add any acid or base to it, you're going to shift that equilibrium slightly, but it's going to end up fighting your pH change, isn't it? Because it's going to consume that H plus you add. It'll consume that OH minus you add, right? Okay. Now, one of the things I want to point out here is people all the time have a blind spot when I say this, which is the definition of a buffer system. If I put an acid, let's say I put 1 mole of acid in, and then I neutralize half of that, what have I effectively done? Well, I've effectively formed a buffer, haven't I? And that, yes, that would form a buffer, okay? So you can put the acid, neutralize half of it, and that's going to give you half conjugate base then, isn't it? And so that would form a buffer system, okay? It ends up being like this blind spot that people develop whenever they start this. So keep in mind, you can neutralize a portion of it to form your buffer system, okay? All right, so buffers are incredibly important in biological contexts. Again, they're going to follow all of the equilibrium reaction material that we've covered so far. They are going to help reduce the change in your acidity for your blood, for example. That's one of the reasons why your pH doesn't normally change much in your blood because you have a series of buffer systems actually that are in your blood that are going to resist the pH change. Again, Le Chatelier's principles applies to buffer systems. So if you have an acid with a pKa of 4 and its conjugate base has a pKb of 10, then the fraction of the acid that it associates, if you have 0.1 molarity of the HA, would be this formula right here. The fraction of the conjugate base that reacts with water would be this amount right here. And that's what you're really doing when you're forming a buffer system. You're putting these two equilibriums together. Okay? All right. Now, notice that because this pKb here is 10, this actually only does a very small amount of association. So we only get 0.0032%. Okay? If we add a acid and its conjugate base together, remember that common ion effect you used to do in general chemistry too? It's a common ion effect, isn't it? And so that actually ends up blocking off a significant amount of the acid and base from doing their reactions because you have that common ion effect. Okay? That's what's making that buffer system so difficult to shift, is the common ion effect, Le Chatelier's principle, equilibrium. Okay, so your Henderson-Hasselbalch equation is going to be the rearranged form of your Ka. You probably recognize this Henderson-Hasselbalch equation from other courses and from previously. This is the typical Henderson-Hasselbalch equation right here, by the way, for the A minus, the conjugate base here. This one is the same reaction, same Henderson-Hasselbalch. We just have labeled this base up here, and then this is conjugate acid. Notice it's always base over acid either way, though. Okay? Okay. By the way, if I wanted to flip these terms in here, what would I do to my Henderson-Hasselbalch? If I flip these terms here, this just becomes negative. Okay? Okay. It's a little trick you can play if you end up with wanting it to use it for different purposes. Okay? All right. So it's pH equals pKa plus the log of the base over the acid. Okay? Now, this is actually if you include the activities here. So again, we just add our activity coefficients here, and that's the only change we make. Okay? All right. Now, if we look at this Henderson-Hasselbalch equation, it is not an approximation. It's just a rearrangement of that equilibrium expression. The approximations we make are going to be the values of the A minus and the HA. We typically, in a Henderson-Hasselbalch, go ahead and use the formal concentrations of these to simplify this equation. Okay? So the base equation, not an approximation at all. Okay? But how people typically use it is an approximation. So you got to watch out for that. So again, this would be the approximation if you were doing this for an acid. Notice that nothing else is the approximation. What is approximation is using the formal concentrations of the conjugate base and the conjugate acid. Okay? The reason people typically do this is because you add formal concentrations yourself of both, right? So you typically put half and half in. And the difference they're going to shift is very small. And so usually this approximation works very well. Okay? So this is very reliable, actually, as long as the pKa is less than or equal to 7. So when the buffers, the Fa minus over the Ka is greater than 20. Okay? So if you take this and you take the Fa minus divided by the Ka, and it's greater than 20, this approximation is going to work very well. And that's how you can actually judge whether you've approximated correctly. This is the one for the base, by the way. And so you'd have the acid form here that you're dissociating to, or you're associating to, excuse me. And this is going to be divided by the Kb. If that's greater than 20, again, your approximation will be good. You can use your formal concentrations here rather than having to solve out for their equilibrium concentrations. Okay. So if the A minus and HA are equal in the Henderson-Hasselbalch, what happens? Well, this would be 1 here, right? The log 1 is 0. And so the Henderson-Hasselbalch turns into pH equals pKa when you have the acid and its conjugate base equal. Okay? So if we look at this right here, a 100 to 1 ratio of the base to acid is going to give you your pKa plus 2 for your pH. See that? If we have a 10 to 1 ratio, you're going to have your pKa plus 1. Okay? And if we have a 1 to 1 ratio, we're going to have the pKa equals the pH. Right? And everybody in biochemistry recently used this. You guys have had fun with this lately. Anybody not in biochemistry, you've done this in general chemistry, but you may not remember it, but it's fair. Yeah. This is why if you ever try to get the pKa, what you can do is you can get the equivalence point, go 1/2 the volume for that, and that's the point that the pH is going to equal the pKa. Okay? Because 1/2 the equivalence point is a 1 to 1 ratio, isn't it? All right? And that region around that 1/2 equivalence point is your buffer region. Okay? It's where you're going to have your maximum buffer capacity. You're going to have your most buffer-like region. Okay. Anybody have any questions about the Henderson-Hasselbalch so far? Really quickly, test yourselves, plug that in, find out if you understand, if you're having any issues, if you have no idea what's going on. The pKa here is 7.53, if you look that up in your book, in Appendix G. Everybody got a pretty good grasp on the formula and tried it out now? Okay, ready? The big reveal. So if we plug this in, 6.2 for the pH, pK is the 7.53, and then we get the log of the base form over the acid form, right? We solve that, we end up with negative 1.33 equals the log of that. Okay. We go ahead and take our solution. So remember, to get rid of a log, you take 10 to the power of, right? So we take 10 to the power of both sides. That's going to give us 10 to the negative 1.33 equals our concentration of base over acid. So that's going to give us a ratio, right? And that's the answer. Okay, tris, very widely used buffer. If you do anything in biochemistry, you've probably used tris buffer to some degree. We actually used it to standardize solutions a while back at the beginning of the semester. That was that one thing I was heating and you took it out of the heater. Okay. So when you were doing those titrations of the tris, you were hitting those buffer regions. Remember that? And the pH was going up very slowly. That's what this was. Okay. Does anybody have any questions about this? Okay. Don't forget, you can also, of course, solve this with grams. You can take the molecular weight of tris and find out the amount of moles, right? And if you have the volume, that's going to give you concentration. Okay. You can work the Henderson-Hasselbalch in moles. There's no reason that you can't, because you're forming a single solution that will have a single volume, right? And so the acid-base concentrations in your solution, both of those have the same volume term, don't they? So if you plug in moles here, this will solve out just fine. You'll have no issues at all. Okay? But they have to be a single solution. Is that making sense? Okay. Okay. All right. Remember, the pH of your buffer is going to be nearly independent of your volume because your volume is the same for both of these. So notice that volume actually ends up canceling out in this equation. So all that really matters is the moles of the base and moles of the acid. Okay? And they have to be a conjugate acid-base pair. All right. Okay. Now, remember that when we add strong acids or strong bases, these are essentially going to be completely disassociated because that equilibrium constant is very large. Okay? And so if you have the tris, for example, the equilibrium constant right here for HCl versus tris, that HCl is going to be 1.2 times 10 to the 8th, right? And so because it has such a huge equilibrium constant, what we're going to do whenever we add a strong acid or strong base into these solutions, these buffer solutions, is they're just going to fully dissociate, and they're going to neutralize however much acid or base it takes to neutralize those. Okay? And so, again, remember, you would just add them straight up as if they're this form right here. Okay? You would completely neutralize that amount of your acid or your base, your weak acid, weak base. All right, so again, the reaction of a strong acid with a strong base, this is going to be even more complete. So if we have a strong acid with a strong base, we can just do the water neutralization reaction right here, which is H plus OH minus gives you water. Okay? And this is actually the flip reaction for that autoionization reaction. Everybody see that okay? And so this is actually going to be 1 over kW, which is 10 to the 14th. And so this has a huge equilibrium constant, and we're basically go all the way to one direction. Okay, we're going to have very, very little of it left over. Realistically, the only stuff we're going to have left over for the H plus and OH minus, if we add equal amounts of HCl and NaOH, any strong acid, strong base pair, is going to be the autoionization equilibrium. Okay, so you'd expect 10 to the negative 7 of each of these concentrations left over. Okay, so what volume of the 0.5 molarity NaOH should be added to 10 grams of tris hydrochloride to give the pH of 7.60 and a final volume of 250 milliliters? So how do we start this problem? We need to get into moles, don't we? Okay. Right now we have grams of tris, right? Everything else is related to moles, isn't it? And molarities. Okay, so we need to take 10 grams and we need to divide it by the molecular weight, right? And that's going to give us our moles. Okay. Once we have our moles, we can actually work this problem mostly in moles to start this off. Okay. And so that's our moles of our tris right here. Our initial is going to be that number of moles that's from the grams that we added. It's going to then react with the OH minus and giving us the conjugate acid here, the base without the H plus. And so our final moles is just going to be our initial, our formal, right, minus whatever change we get from the OH minus being produced. Okay. Okay. So in this case, right here, we know the pH, right? We know the pKa. We know the moles, don't we? Okay. So we know most of these terms, right? So we can go ahead and use the Henderson-Hasselbalch here. Our pH gets plugged in here. Our pKa gets plugged in right there. This is plus the log. Well, we need the concentration of the B yet, and we don't know the concentration of the BH plus yet. Okay? And so what we need to do now is solve. So we subtract this over. That gives us a negative value right there. We take 10 to the power of both sides. That gives us this equation right here. And then there's two different ways we can go from here. So if you want to be sure, you have to do the quadratic formula, right? Get everything on one side so it's set to 0, and then solve using the quadratic formula, okay? The other way you can do this is you can assume this is going to be not large enough to change this bottom here. And then you can just solve for x by multiplying that over, right? In this case right here, this value is too large, so that would be a bad assumption. Does everybody see that okay? So this would be a case that you'd do that, you'd mess up and go, whoops, that's too big. It's not 1%, is it? And so you'd go back and use the quadratic formula. Okay? Okay. Anybody have any questions so far? Now, in this formula, this is how much NaOH we have here. So that gave us X here, which solves for the final moles of the BH plus and B here, right? Okay. So what we need to do to figure out the amount of NaOH is we have our moles, don't we, that we need to neutralize here. See, that's our moles that we need to produce. And so all we need to do now is we just need to take that number of moles and solve out for the number of milliliters from it. So we take that number of moles, that's the number of moles of NaOH we need, we divide it by the concentration of the NaOH. And that's going to give us our liters. We convert that to milliliters, and that's how much NaOH we have to add now. Okay? Okay, did I lose anybody? Okay. Now, when we actually prepare buffers in real life, typically the easiest way to do this, unless you have both species just lying around the lab, that's not as common as you might think. Usually the easiest way to do this is actually to weigh out the what you want to use for the buffer. In this case, we're using tris hydrochloride. We dissolve that in water, and then what we do is we put an electrode in there to measure the pH. We want our pKa and pH to be equal. So we take our pKa value, we add, in this case, we're going to add NaOH because we need that pH to go higher. And we add NaOH until the pH equals the pKa value. Okay? And that's going to give us our buffer system. You can make buffer systems that have a pH that is not exactly the pKa, but it should never be more than 1 unit away from the pKa. Okay? Because your buffer system is going to be very weak if you do. If you do 2 units away from the pKa, your buffer system is going to break in one direction very easily. Okay? Okay. Now, whenever we do this, do not simply add the calculated quantity of NaOH. It will not give you the desired pH. There's quite a few sources of error here if you just try to do this predictively and really without getting experimental feedback here. These errors are the activity coefficients. You probably did not do this calculation with the activity coefficients. And if you did, it would have taken a lot of time to do, right? So it's so much easier to stick a pH meter in there and just change your pH to be equal to pKa. Okay? The temperature might not be 25 degrees Celsius. This would be a mismatch to the pKa table, and thus you would have the wrong calculated numbers, right? And very likely, you're in a lab, it's not 25 degrees Celsius, is it? It's usually less in most of these labs. Sometimes it's way more, right? Approximations are being used. Remember, you're approximating the HA usually. You're approximating the A minus with those formal concentrations. Okay? And so that is going to give you some error, though these are typically the larger errors that get included in this. The pKa list in the table is probably not what you would measure in your specific setup. There's a lot of things that can go into a pKa, including the temperature, of course, which we've already talked about. But all right, so let's talk about buffer capacity. Buffer capacity is typically shown as beta. That's buffer capacity. And that's going to be how well a solution resists pH changes in pH when you add a strong acid or a base. A good example of this is actually environmental regions. For example, has anybody ever heard of the Shield Lakes in Canada? No? Okay, it used to be very, very famous because they were incredibly pure water. Okay? And so the water was incredibly pure, but one little problem. Purity means that it has very little buffer in it, right? And so it has very little buffer capacity. Okay? And what that meant is that when acid rain started getting in Canada, the pH of the Shield Lakes ended up going down to pretty acidic levels, actually. Killed off a bunch of fish and stuff, and it was really bad. Okay? Caused a lot of problems. And that's all because they have very poor buffer capacity. On the other hand, if you look at Louisiana, the the swamps actually have great buffer capacity. And so the swamps have really survived some pretty nasty drops in pH because they have huge buffer capacity, right? And so, like, they're really absorbing a lot of hits. They have absorbed oil spills, acid rains, and have like little speed bumps. No effect. So those swamps, man, they have great buffer capacity. Okay. Now, the maximum buffer capacity increases with increasing formal concentration of your buffer. So keep that in mind. Your formal concentration of your buffer times 0.58 typically is going to be about equal to the buffer capacity. And this right here is your pH versus buffer capacity right there. Okay. All right, this is the buffer capacity is the real reason we always want to choose a buffer that's very near the pH we want to have. Okay, so when you're making a buffer system, you always want that buffer pKa to be very, very close to the pH you want that buffer system to have, whatever pH you want to keep constant. Okay. So if they're exactly aligned, we're going to get our buffering capacity as about 0.58 times the formal concentration of the buffer. Okay, that's going to be our relative buffering capacity right there. If we start getting further away from that, look at what happens to our buffer capacity. So if you go a full unit off, you're only 0.33 of your possible buffer capacity, aren't you? So you've actually lost a tremendous amount of that buffer capacity, just 1 pH unit off. 2 pH unit off, you basically don't have any buffer capacity at all on one side. Okay? And so if you add any significant amounts of acid or base into it, it probably is going to break your buffer. And you're going to have pH change. Significant pH change. Now when I say they resist pH change, everybody understands that they don't just like no pH change, right? It's just very small amounts of pH change, and then it will skyrocket after you break your buffer. Okay? Like you saw with the titrations. Okay. This is actually how you would calculate how much pH change you would get. Remember, you just run this through your equilibrium, and so you can just use your pKa here and look at how much you would neutralize the species. So let's have a buffer solution containing 50 millimole of the buffer species and 50 millimole of the conjugate base of that. Your pH is going to equal the pK of the buffer. So how much would that change if you added 20 millimole of some acid from some sort of chemical reaction? Okay. So what we would do here is we would take, again, our pH would equal pKa, right? So that's all we have to do is we just have to take the difference in the pK and pH. And so we take 20, we add that to the acidic species because we added acid, right? And then it's going to reduce the base species by 20. Everybody see it okay? So we'll end up with 30 versus 70. 30 of the base, 70 of the acid species. Again, those are just those numbers minus the 20 plus the 20. Okay. Okay. Once we add those in, what we're going to get is we're going to get the pKa minus 0.37. That's going to be our pH there. And so your pH units are going to end up dropping 0.37 units, right? And so notice that, yeah, you resisted that pH change pretty reasonably, didn't you? Okay. That was within your buffering capacity. All right. Now, the buffer pH, this does depend on your ionic strength and temperature. Remember, temperature changes those pKa's, right? When we're looking at those pKa's, they're actually the activities, right? They have the activity coefficients in that formula if you calculate them out properly. And so your ionic strength and your temperature both change that pH of your buffer. So when you prepare a buffer, calibrate its pH at the temperature you plan to use it at. So if I make my buffer at lab temperature, but I plan to run a reaction at 50 degrees Celsius, am I going to be okay? No, I very likely am going to have a different pH than what I expected to have, aren't I? Okay? I'm going to have a very significantly different pH. Okay? What if I added a bunch of salt to it? Hey, I want this reaction to go faster. I'm going to add a bunch of NaCl to it. Is that going to be okay? No, the ionic strength is going to change my buffer pH, right? I could end up completely out of range of what I need for that pH. Now, one thing that has fairly minimal effect on the buffer pK is pressures that are below 100 megapascals. Okay? Mega being a million, right? And that's because you're in liquid systems. Liquid systems don't have a great deal of compression. Everybody's tried to use your water bottle and squeeze, right, when it's closed. And you basically get nothing, right? It almost doesn't squeeze at all because it really starts resisting you fast, doesn't it? Okay? Liquid systems do not compress well. They're very difficult to compress. So it makes very little difference on them. If you're in gas systems, it can actually make a difference. And so this is going to mostly be ignored here. These are some common pKa values for common biochemistry buffers. They're summarized in your book there. And you can print these tables if you ever need. Fairly useful whenever you're trying to work in biological buffers. So this is the pKa prime. This is typically going to be something that you would use at like a physiological condition, but prime technically just means any modified set of conditions. Okay? Though if you're doing stuff in biochemistry, it's going to mean physiological conditions because they use the prime for physiological there. Okay? And so this right here is a buffer system, MOPS. It's at 37 degrees Celsius at 0.1 molarity ionic strength. And so we can actually plug this in to this equation right here, which actually helps us adjust this equation we've been talking about, the pKa equation, by these factors. Okay? And so in table 9.3, which is the one I just gave you there, the pKa prime of MOPS at 25 degrees Celsius is this value right here. This will be the ionic strength, is 0.1. So it's delta pK over delta T is this value right here. Okay. So what we're going to do is we're going to use this equation here. The pK at 37 degrees Celsius equals the pKa prime at 25 degrees Celsius plus 37 minus 25 over that shift factor for that temperature, which is this value here from the table. Okay. So we take those difference, we multiply by that, and then what we're going to do is we're going to subtract the table value there. So we get negative times a negative. That's going to give us a positive here. We add that value to the 7.08 from the table, and that's going to give us 6.94. So that's going to be our pKa at 37 degrees Celsius. Okay. Now, keep in mind, dilute solutions or extremes of pH, the concentration HA and A minus, are not going to be equal to their formal concentrations. They're going to be significantly different. Okay? And so if we mix formal concentration moles of Fa and A minus of the salt Na plus and some anion, which is a strong electrolyte, the mass and charge balances are going to be this equation right here. So the formal concentration plus the formal concentration of the A minus equals these concentrations added together. Okay. The charge balance is going to be this, and this is just all the charged species, right? Okay. So we can actually substitute this in, and we get this equation right here. So again, Na plus has to equal the A minus concentration, because that's where we got our A minus concentration from here. Okay. And so what we're going to find is that we're going to have the concentration of HA. This equals the formal concentration of the HA minus the H plus the OH minus. Okay. All we did was substitute this into this, right? And then this one right here, this is going to be the concentration of A minus, is the formal concentration plus the H plus minus the OH minus. Okay. All right, so does anybody have any questions about any of this? Did I lose anybody here? Okay. Now, let's quickly do this question, and then we're going to just move on, okay? Unless somebody has questions about it. So try this equation right here. What will be the pH of 0.01 mole of HA? It has a pK of 3, and 0.005 moles of A minus that are dissolved in water to make a 1 liter solution. So notice that this would be like your classical ice table problem, right? But I've given you another way of calculating this that's faster. Okay? So what do we have to do? Well, we have to look at this and see, well, what sort of system are we looking at? Okay? Do we have to use the full quadratic, or can we do the simplification? That'd be always a good way to start this out. Okay? And so the Henderson-Hasselbalch, we can approximate it when our A minus concentration is greater than our Ka by 20 times. We take our Fa concentration, which is that 0.005 value right here. We divide it by 10 to the negative 3, and we find out that, well, we're only equal to 5, aren't we? So we're not greater than 20. Okay? So we actually have to solve the quadratic here. We're going to have to do this the long way. So our solution is going to be acidic because our pKa is going to be 3 for this, right? Telling us that we have a reasonably strong acid. Okay? And so the pH is going to be approximately the pKa for this because we're pretty close to the same amounts here. We don't have a huge amount difference between the two species. We can neglect the OH minus concentration because we're in an acidic solution. It's going to mean we have very small concentrations of OH minus, right? And so we're going to go ahead and set our equations, 9.23 and 9.24. Our H place concentration is going to equal X. We can use the Ka equation to find that H plus concentration. And so again, here's our equilibrium that we're using right here. This again is going to be the formal concentration we can put in for here. This is going to be X for H plus, and this is going to be the formal concentration of the A minus here. So we have our Ka expression. We put in our H plus concentration. This is times the formal concentration plus the H plus. Remember, we got that from here. See that? That's that correction if we're within that range, right? That we can't make that assumption. Okay? Why don't I have the OH minus concentration there? See, I dropped it. What happened? Should have been plus H plus minus OH minus, right? Why did I drop that concentration? If our pH is around 3, what would the OH minus concentration look like? 14 minus 3. So it'd be like 10 to the negative 11, right? If I subtract off 10 to the negative 11 out of this value here, is that going to change things significantly? No. No, I can ignore it, right? Goodbye OH minus concentration. Okay? Because I'm doing addition subtractions, I can ignore very small values, can't I? Okay? So anywhere I do an addition subtraction, I can ignore the small values. Okay, so this is the F formal HA right here. Remember, that's minus the H plus the OH minus normally. Okay? See that? We have our acid, that's minus the H plus the OH minus, right? Because the acids produce the H plus. And so I can take my formal concentration HA minus the H plus, and that gives me this value here. Now, this is just stated in these abstractions right here. That's all that is. Okay? So we put X everywhere the H plus is, then the formal concentrations, which are values we've been given in the problem. These values. Okay? All right, so all we have to do now, we plug in our formal concentrations, we solve this so that we get it in the form of a quadratic. Okay? And so we distribute this through FA times X plus X squared, right? This doesn't need to be distributed, this just multiplies over. And this is what we get once we do that work. Okay? And again, that's in the form of quadratic, right? All right, so what we're going to do next is we're going to go ahead and solve our quadratic. And so if we plug our quadratic in here, we're going to get this right here. Notice that's just the quadratic, right? I've just done it in abstraction rather than numbers. Okay. Again, if we write this in terms of pH, though, what we're going to do is we're going to take the negative log, aren't we? Okay. So the negative log of that side is pH. Negative log of this side gives us this. So, using the equation 926, which is right here, once we plug our values in, we solve this. I would not actually plug all this in at once. I would have normally put the values in each step and solved it down each step as much as possible. It's a little easier. But what we find here is the pH is actually 2.87. And so the HA and the A minus are not what we mixed. Notice that we have a pretty significant difference of concentration here, which is you take the formal concentration minus the H plus here for the HA. The A minus concentration is the formal concentration plus the H plus. And that gives us these. Okay? All right. Again, the HA is too strong in this case. The concentrations are too low for your HA and A minus to be equal to their formal concentrations. That's what we tested here. If it had been greater than 20, we could have not done all that work. Yeah. Which would have been nice, right? Okay, this is a buffer summary. This is actually how you do this in Excel. I do highly recommend you try this out because in actual work, this is so much faster than solving this out. Okay? It's way faster in Excel. Okay, does anybody have any questions? All right, everybody ready for the exam? Yeah? Uh-huh.
With Canvas being down, how, like, I haven't done review 2 yet.
Mm-hmm.
So, like, is there a way you can post that we could access it without going through Canvas?
So if you have your password for the site, Achieve, then you can access it no problem. It's your school email. You can actually try to access it with Achieve, and you should be able to get around having to do it through Canvas. Now, considering that the fault is actually Amazon server, AWS, I would highly suspect this is going to be solved by tonight.
Okay.
Yeah. Like if they don't solve it, they're right now, you know, they're losing like billions of dollars every hour, right? I don't know if you guys know that, but This is likely in the like millions of dollars a minute sort of thing that they're losing right now. So should get solved pretty quick, actually. But you never know, I guess. Good grief. Let's look at that real quick. Have you already tried Canvas already?
Yeah.
Just now? Okay.
What are the chapters, exams? For? 5 to 9?
Yeah, so it is 5 through 9. Mm-hmm. Those are the chapters the exam's over. And so if it's not solved fairly quickly, what I would probably do is contact Achieve and see if you can get a way to sign in that's not. Okay? Just send an email. Let me see what Achieve looks like. Let me double check that it's not.
I'm also sorry, is this test all multiple choice like the last one or no?
Yes.
It's all multiple choice?
Mhm.
Okay.
Yeah. It's fairly rare for me to do not multiple choice here because, honestly speaking, the multiple choice does just as well as the non-multiple choice for most of these. They're pretty like, you got the answer or not.
Is there anything you're opting out?
Hmm?
Is there anything you're opting out?
I can't make you do Excel problems. I mean, it really is. That would be the only one that I would like do something.
I assume just like really long problems that would take us an hour.
Yeah, I can do parts of it,
Yeah.
but I can't do the full thing. Yeah. So, yeah, expect like parts of those. But yeah, I can't make you do a full, long, hour-long problem. It's just not gonna fly. So I'll like start you somewhere in the middle, then you have to do the next steps or something. Yeah. There's a little bit of definitional sort of stuff as well. The homework, the expectations are when I give you a problem that requires the definitional that you'd understand the definitional to be able to do the problem, right? And so, yeah, in the test, I break those apart a bit more. Okay?
And will we have as many like lab procedure questions, like how to make a buffer, how to titrate things, like the steps that we need to do?
Not quite the number you had last time,
Okay.
because last time there's like a whole chapter on that, right?
Yeah.
So we had a whole chapter of questions in there that's what that was, lab procedure stuff. Yeah. And there wasn't anything I could add other than read the steps.
Yeah.
So, the Achieve is working. It's a little buggy right now, but it's working. Okay. So if you go on there, you should be able to sign directly through into the Achieve if you want. Assuming you ever saved your password.
Yeah.
If you did not save your password, you can do it several different ways. If you want to relink them later, once everything gets resolved, you can set forgot password and then reset it. Yeah. That'd be the fastest way to resolve that. Okay, next time we're going to start on chapter 10. And then I would appreciate if